Hi, welcome to the solution for the in-class design problem from lesson 30. We're going to do the analysis for the design, of a two-beam platform. Since the beams are evenly spaced over the 4-foot width, it gives us a 24-inch on-center spacing between the beams, which leaves 12 inches on the outside of each beam. Cover that entire 4-foot width of plywood. This then gives us a tributary width for each beam of 24 inches. Now we're going to initially neglect the self-weight. We'll come back and deal with self-weight in just a while. But let's talk about the other loads that we have on the structure. We have the weight of the cadets, and if we assume a 170 pound per cadet, we've got 18 cadets in a typical CE 300 classroom. That gives us a total of 3,060 pounds on the platform. We also have the weight of the plywood that we need to account for, and we're told that that is 65 pounds. If we combine these, we get a total weight of 3,125 pounds. We know that that weight is distributed over the entire 4-foot by 8-foot area of the plywood, which gives us a load of 97.65 pounds per square foot. Now, since we have a 2-foot tributary width, 2 feet times the 97.65 pounds per square foot gives us an applied load, distributed load, uniformly distributed load of 195.3 pounds per foot. With that load of 195.3 pounds per foot, it is now time to draw our shear and moment diagrams. Noticing that we have a symmetrically loaded beam, we know that the reactions at both ends are going to be equal in magnitude, and they will come out to be 732 pounds each, found by taking the distributed load of 195.3 pounds per foot times the total length of 7.5 feet. And half of that total load flows into each support reaction. So on to our shear diagram. First, we begin at 0. We are dealing in units of pounds. The reaction, 732 pounds, causes a jump to a positive 732. Since we have a uniformly distributed load, it means we have a linear shear diagram with a constant slope of 195.3 pounds per foot. Over the course of that area, or over the course of that length, that drops us to a negative 732 pounds. And then that support reaction brings us back up to 0, so our shear diagram closes. In order to build our moment diagram, we need to find the area of each of these triangles, 1/2 of the base times the height being 732 pounds, the base being half of 7.5 feet, gives us an area of 1,372.5 pound-feet. The area in this piece is negative 1,372.5 pound-feet. Our moment diagram is going to be in units of pound-feet. We begin at 0, and we know that where the shear is 0 is going to be our maximum moment, and in this case our maximum moment is equal to 1,372.5 pound-feet. Since our shear diagram is linear, our moment diagram is going to be parabolic. And let's label these for completeness sake. And we are then ready to move into our design. Starting point for every design is the actual is less than or equal to the allowable. And in this case, we are going to design it for flexural stress. So we're going to compare the flexural stress. In this case, we'll use the equation M over S. And we want to make sure that it is less than or equal to the allowable stress, comparing it to the yield stress, designing for elastic strength, divided by the factor of safety. We're wanting to solve for the section modulus required for this section, so if we rearrange our equation, find that the section modulus is equal to the moment times the factor of safety divided by the yield stress. Substituting in our values, 1,372.5 pound-feet times a factor of safety of 3.0 that we're given in the start of the problem, divided by the yield strength of 4,900 psi gained from table A-17 in the back of our textbook. And we notice that we have pounds and inches on the bottom, so we need to have pounds and inches on the top. So we'll need to multiply by 12 inches per foot. Therefore, our section modulus must be greater than or equal to 10.08 inches cubed. It's time to generate some options. And we take a look at table A-15 for dressed lumber, and we see that our best option is a 2x8, which has a section modulus of 15.3 cubic inches. Before we proceed with our design, checking it for shear and deflections, we need to double check the self-weight and make sure that this beam can hold not only its own load, the load of 195.3 pounds per foot, and we want to also include the self-weight. If we look in table A-15 again, we'll find that the self-weight is 3.39 pounds per foot of length for a 2x8. So our reactions in this case are 745 pounds, which makes the values on our shear diagram 745 and negative 745, same shape as we had in the previous shear moment diagram. Maximum moment is now 1,397 pound-feet. So if we walk through the analysis, where our starting point is still our actual is less than or equal to the allowable, we want to now compare the actual stress within the beam, including its own self-weight, and make sure that it is less than or equal to the yield stress divided by the factor of safety. Substituting in our values and converting so that we're consistent with units, we find that the actual stress is 1,096 psi, while the allowable stress is 4,900 psi divided by that factor of safety of 3, which is a value of 1,633 psi. So our actual is, in fact, less than or equal to our allowable. So our design is okay for self-weight.